Solution number four, because we could use a little bit more trigonometry in our lives. All right. There are many parts of this triangle which move. We've used x to represent the height, the distance of the base from the apex or the center. So those are all height-related uh, solutions. And then the third solution was related to the base. But this time I'm gonna use that angle theta. So that would be half of the apex angle. Well, instead of using theta to represent the entire angle at the apex, half of that would suffice. Like the apex angle is just going to be double that. And then what the value of how the value of theta influences the figure is, well, of course, the smaller the opening theta, then, all right, I guess it's better to just show it with this illustration. The smaller theta is, then the smaller the base of the triangle becomes, and then the larger the value of theta is. So you get a larger opening with the apex angle. So this is what's gonna happen. All right, now, as in the third solution, we may assume that because we're interested in the triangle isosceles with the largest area, we may assume that the base is below the center. That was an observation from solution number three, which we did not use in the first and second solutions. But in case it was something that you recognized, then you could have ended up modifying the solution to solutions one and two. So I don't know, that could have maybe led us to change the domain. But then in the end, the answer should still be the same. We should still end up with the usual conclusion. Our isosceles triangle would have to be equilateral. But anyway, because the base would go no higher than the center, all right, what that tells us is that the angle theta would be, well, it would have 0 as a lower bound. So the lower bound of theta is 0, and then what's the upper bound of theta? So consider this extreme situation where I can't bring this movable point higher than the center. So if you look at this figure, this would correspond to the case where, because this space is on the diameter, you actually have a right angle here. So that means angle theta is 45 degrees, or in radian measure, that would make it pi over 4. So here you go, theta is from 0 onwards to pi over 4. Now, if you did not recognize that it's okay to let the base only run through the lower semicircle, if you're still open to the possibility of the base of the isosceles triangle navigating through the upper semicircle, then you would then be open to theta not ending at pi over 4, but in the long run approaching pi over 2, a 90-degree angle. All right. So again, many different solutions. In the end, if you do it correctly, you're going to end up with the right answer. So let's agree that theta, let's set theta to belong only to the interval 0 to pi over 4. All right. So, well, this time we're going to use theta to represent the area of our triangle. Instead of using the formula 1/2 base times height, all right, what we're going to do is, sorry, I don't have the illustration here, but let me just describe it. One formula goes like this. You take an included angle, then take the sine, trigonometric sine function, multiply by the adjacent sides, and then half of that. All right, that would give you the area of that triangle. So in this case, what we gotta do is, therefore, because we recognize this angle is going to be double theta, then we just need to figure out the length of this side and this side in terms of theta. But fortunately, because you have an isosceles triangle, these two sides the left and the right are going to be congruent. So of course, you just only need this right side. And then to figure that out, we could use the symmetry of the situation. How exactly? All right, this triangle on the right, bounded by these two radial segments. If you bisect it in the middle, so there's supposed to be a 90-degree angle here, and then if you identify this black segment, that's going to be half the side. If the side of if this side I'm tracing is length s, then this black segment is s over 2. And so now if you look at this right triangle, you could all relate them by this trigonometric equation. The cosine of theta is adjacent s over 2 divided by r. All right, which means that the side is 2r times the cosine of theta. So yippee, now we have the following area formula in terms of theta. As I described earlier, it's 1/2, and then the product of these two adjacent sides. So s times s, so it's the square of this, the square of 2r cosine theta, multiplied by the sine of the included angle, so the sine of double of theta. So of course this can be expanded, but I'm anticipating what's going to happen afterwards. We're going to have to differentiate. And then we're going to end up having to solve a trigonometric equation. Now, currently we're seeing two angles, theta and 2 theta. Towards the end, we're going to have to do a conversion, probably, so that all angles would be consistent. So, before we carry out the differentiation, why don't we replace sine of 2 theta as early as now with an equivalent expression involving only theta standalone? Alright, so you have from 1/2 times s squared, 2r squared cosine squared theta, and then from from the sine double angle formula, sine of 2 theta is double, sine theta cosine theta, then algebra your way through this, you get 4r squared, and then a single sine, and 3 cosines. And then use the product rule for the derivative, so you have a 4r squared sine theta differentiated will give you 4r squared cosine theta with cosine cube copied. And then next we copy 4r squared sine theta and then differentiate cosine cube. So 3 brought down cosine squared. That's the derivative of cosine, which is negative sine theta. And then progressing from this point can be done much more easily by extracting common factors. We have 4r squared, of course, and then cosine squared. So let's factor out 4r squared cosine squared. Verify the other factor would be cosine squared minus 3 sine squared theta. Now, the domain of cosine and sine is r, all real numbers. So there is no critical number that would make the derivative undefined. So next question, when would the derivative be equal to 0? Oh, it's when the factors become 0. So it's either cosine squared theta is 0. All right. Okay, I just pointed it out. A prime non-existent. Nope, never going to happen. So when is the derivative equal to 0? It's when cosine is 0 or when this difference is equal to 0. In other words, cosine squared theta equals 3 sine squared theta. So let's explore the solutions of these trigonometric equations. Don't forget the domain of theta is from 0 to pi over 4. It's not even the entire first quadrant, but just half of the first quadrant. Cosine theta is 0. First thing that comes to mind is pi over 2, but that's beyond this. No angle here has a cosine equal to 0, so that's a dead end. So now, when is cosine squared theta equal to 3 sine squared theta? I guess one option is to replace cosine squared with 1 minus sine squared. So you only have to deal with one trig function. Or alternatively, replace sine squared with 1 minus cosine squared. So there's only one trig function to deal with, not the two that you see here. Or alternatively, if you divide both sides by cosine squared and also by 3, remember sine over cosine is tangent. Here's what we end up having. Tangent squared is 1/3, which means that when you take the square root of both sides, tangent theta will be plus or minus 1 over the square root of 3. But keep in mind theta is in the first quadrant, and in the first quadrant, all trigonometric function values are positive. They're never negative. So tangent theta is positive, so we only take 1 over the square root of 3. And then this doesn't give us much room to wiggle through, so, which is a good thing. We end up having to identify only one angle. It's pi over 6 or pi over 3. Pause the video, think about it. Do you have your answer? Theta is pi over 6. So, the usual scenario, or evaluate A at the endpoint 0 and pi over 4, and also at pi over 6. I'm going to leave the verification to you. Again, you get your absolute maximum from the third area computation. And so we know eventually the implication, the triangle has to be equilateral, but it's fun to point out that that conclusion comes more easily now, because if theta is pi over 6, that's the value of theta that maximizes the area. If the right side is pi over 6, then the left side has the same value. So that would make the apex angle double that. It would be pi over 3 or 60 degrees. And so from 60 degrees, you have 120 degrees remaining to be shared by the base angles, which are congruent. So therefore, they would also have to be 60 degrees. So if the three angles are 60 degrees, then our triangle is equilateral.